Let's consider some practical uses of matrix mathematics in a variety of settings, along with a brief introduction to matrices. Matrix mathematics applies to several branches of science, as well as different mathematical disciplines. We see the results of matrix mathematics in every computer-generated image that has a reflection or distortion effects, such as light passing through the rippling water. Before computer graphics, the science of optics used matrix mathematics to account for reflection and for refraction. Matrix arithmetic also helps us calculate the electrical properties of a circuit with voltage, amperes, resistance, and etc. Matrix mathematics simplifies linear algebra, at least in providing a more compact way to deal with a group of equations of linear algebra. For example, say you have a complicated network of resistors and you apply a potential difference to two junctions in the network, say connecting them to ends of a battery. What is the current going through each resistor? If the network can be split up into series and parallel combinations of resistors, it's easy to solve, but in general, it is not possible to do this. Then, the only way to find a solution is linear algebra. You have n unknowns, the relative potential at all the other junctions, and n equations from Kirchhoff's current law at those junctions, and you can solve the system to find the unique solution. The following circuit has 7 unknown currents marked I1, I2, I3, I4, I5, I6, and I7. If we know the simultaneous equations involved, we will be able to solve the system using matrices. Recall Kirchhoff's laws. Kirchhoff's current law: total current entering a junction is equal to the total current leaving the junction. Kirchhoff's voltage law: equal, in any closed loop network, the total voltage around the loop is to the sum of all voltage drops within the same loop. The circuit equations using Kirchhoff's laws are -26 is equals to the product of 72 and I1 minus the product of 17 and I3 minus the product of 35 and I4. 34 is equals to the product of 122 and I2 minus the product of 35 and I3 minus the product of 87 and I7. -4 is equals to the product of 233 and I7 minus the product of 87 and I2 minus the product of 34 and I3 minus the product of 72 and I6. -13 is equals to the product of 149 and I3 minus the product of 17 and I1 minus the product of 35 and I2 minus the product of 28 and I5 minus the product of 35 and I6 minus the product of 34 and I7. -27 is equals to the product of 105 and I5 minus the product of 28 and I3 minus the product of 43 and I4 minus the product of 34 and I6. 24 is equals to the product of 141 and I6 minus the product of 35 and I3 minus the product of 34 and I5 minus the product of 72 and I7. 5 is equals to the product of 105 and I4 minus the product of 35 and I1 minus the product of 43 and I5. What are the individual currents from I1 to I7? We solve this using the following. Let A be this matrix. Let B be this matrix. and let X be this matrix. In this problem, we're going to use the Gauss-Seidel iterative method. Recall the formula? The Gauss-Seidel method is a technique for solving the n equations of the linear system of equations Ax is equals to b, one at a time in sequence, and uses previously computed results as soon as they are available. Suppose let's start with the initial solution. X raised to 0 contains 0, 0, 0, 0, 0, and 0. Using the following C++ program, we get the following results currents in this circuit. So, the I1 is equals to negative 0.4680, I2 is equals to 0.4293, I3 is equals to 0.00005, I4 is equals to negative 0.22224, I5 is equal to negative 0.2785, I6 is equals to 0.2112, I7 is equal to 0.2091. Thank you. I hope you learned something today. Until next time.